Welcome. You would see the relation between Feynman-Kac formula and the formula for variations of constants. Okay, so these two things we are going to see, and we are going to build the relation using some new definitions. So here we are going to talk about Markov semigroup. It is not that we have never discussed it, but we have discussed it always in disguise, and we have discussed very briefly for some special cases. So I would try here to give broader settings for that. Okay, so I mean the background, let me tell that when we have introduced semigroup of operators, that time we also have given some examples. Example from translation semigroup, example from finite state continuous time Markov chain, etc. So there we have already shown what is the semigroup for corresponding dynamics, and then also we have obtained the generator there. So but here we are treating for a general broader setting. So let xt be a Markov process on a Polish space script x. What is this? What is a Polish space? A Polish space is a complete separable metric space. Okay, so here we assume that t is less than s. Okay, so for t more than s and small x in script x, we introduce this notation small p. So p of s x t dy. P s x t dy. So s and t is like time-like parameter, and x and y is like space-like values. Okay, so this denotes the regular conditional law of xt given x is equal to small x. Okay, so dy is like the measure. Okay, the measure it casts on the range set of the random variable. Which random variable we are talking about? Xt. X is the Markov chain, and for that Markov chain at time t, it is a random variable, and that random variable gives the law or the probability distribution of the random variable, and that distribution is this. Okay, when given that at time s, which is earlier than t, the Markov chain is at position small x. Okay, so this is the kernel. Okay, so let me clarify again. So PSXTB, where B is any Borel subset of the Polish space script x, then PSXTB denotes the probability that xt belongs to B given xs is equal to small x. Okay, so this PSXT dy is called the transition probability kernel. Okay, now Chapman-Kolmogorov equation is the equation which we obtain for Markov chains transition kernel. So that equation is stated below, that PSXT dy, that means the law at time t given that at time s it is at x, is equal to integration psx r dz. So r is the time point in between s and t, prz t dy. So this is the probability distribution of the Markov chain at time t given its location at r time, rth time on z. Okay, so its location at time r is z, given that what is the distribution, and this is saying that given the Markov chain is at x at time s, okay, what is the distribution of this at time r? Okay, so we are integrating this with respect to z. So I mean, this is little vague way of writing, but I should have written small z belongs to this, okay, to denote that I'm integrating through z. So that means that this is time s, this is time r, this is time t. So here the Markov chain is at x, here the Markov chain is at some place z, and here it is some place y. So we would like to understand that the distribution of these given at s it is x. So in between we come here that we find out from here to here, that is p s x r d z gives me the probability coming from here, and from here to here that is p r z t dy, and then we integrate with all possible z. So z belongs to this. We integrate all possible z, then that would give me, you know, the in between from s to t time. Okay, so that is the idea. I mean, this is possibly something which you have all seen in some course in probability theory and stochastic processes before taking this course. So this is Chapman-Kolmogorov equation. Psxt dy is equal to Psxr dz Przt dy, where integration is with respect to the z variable. Now let small f is a bounded measurable map, a real valued bounded measurable map on the state space of the Markov chain. Okay. Now define, why did I take bounded? Measurable I must take because I am going to do integration, but why did I take bounded? Because to ensure that the integration exists, is finite. Okay, so UTSFX, we define U, a new operator, a two-parameter family of operators U. UTSFX is defined as f of y psx t dy. Okay, so it is just integration with respect to the probability measure of f. So this is nothing but the expectation, correct? Because the expectation is, because this is like a density, correct? So this, if you take dy here divided by dy and dy, so that would give you the density of if that exists. Okay, so this is like a density here, and so this integration is just the expectation. So this is actually expectation of f. What is y? Y is the location of the process at time t. So this is f of x, capital X subscript t at time t, given that at time s it is at small x. Xs is equal to small x. So this is the interpretation in terms of expectation. Okay, so this is an operator surely. Why? Because given a function f, okay, which is bound measurable, I get another function of x, because this whole thing is also a function of x. And that is also a bounded measurable function, because, you know, if f is bounded by capital M, the whole thing would also be bounded by capital M. Okay, so that also says that U is actually a contraction. Okay, is a contractive map. Okay, so the operator norm of U is less than or equals to 1. Okay, so we are now going to see more properties of this two-parameter family U. So UTS, so where S is less than or equals to small t, so this is a two-parameter family. So then we use the Chapman-Kolmogorov equation. See, I mean, Chapman-Kolmogorov equation we can easily do, because, you know, that I mean, in between t and s, if you put r there, and then we take conditional expectation here. Okay, so we can use the Tar property of expectation. Okay, and from that, whatever we are going to obtain, if you want to write down in terms of integration, we would come up with this type of, you know, integrations, and then using Chapman-Kolmogorov equation, you can do that. So we get UTT is equal to identity. Why? Because at time t, if the information is given, so if you take xt is equal to small x, then expectation of f of xt is f of x, because xt is given. There is no randomness here. So f of xt given xt is equal to x is f of x. Correct? So then this whole thing is just f. That means this operator is the identity operator. Okay, so UTT-F is f itself. Okay, and then we get further that URS is equal to UTS. Okay, so here that means that given S time, the R is the future and the given R is the further future. Okay, so that thing is UTS. Okay, so you would get all these things. Okay, now if xt is, in addition to the above, is time homogeneous, okay, then we don't need to bother much about the 2-parameter family. We can reduce to 1-parameter family. Why is it so? Because here expression f of xt given x is equal to small x is the same as expression f of xt minus s given x0 is equal to small x. So it does not matter that where it starts from, the location only matters because it is time homogeneous. Okay, so time homogeneous case is much simpler, and for this simple case we can write down u of t comma s as u of t minus s comma 0. Okay, so as I have described in the earlier slide. Okay, so thus this ut0, okay, so 0 is fixed and then we vary t, forms a semigroup of bound linear operators. See, here, so here utr would be u t minus r is comma 0, and this would be u r minus s comma 0, and this would be u t minus s comma 0. So r minus s and t minus r, if you add, you get t minus r plus r minus s, that is t minus s, you get t minus s. Okay, so it shows the semigroup property. Okay, so this ut minus s, ut0 forms a semigroup of bound linear operators on this bounded measurable function on the state space x, okay, on L infinity x. So this is the Banach space we are considering for this setting. Okay, now we have already seen examples of this semigroup for translation and finite state Markov chain. Okay, so we are going to see now some more example. Okay, for Brownian motion. For Brownian motion, what should be the semigroup and what should be the generator? Okay. We have some anticipation that in Brownian motion the half times Laplacian was coming again and again very crucially. So that was also an operator, and that also appears in the martingale problem. So we anticipate that, okay, possibly that should be the generator, but we have never discussed it. So let us do it now more clearly. So for Brownian motion, consider f is in instead of the bounded measurable, so here I'm taking bounded continuous function on R. Okay, so consider f is a bounded continuous function on R, then ttfx. Okay, so as earlier page, we write down that expectation of f of wt given w0 is equal to x. Okay, so this is the operator tt. Okay, so since I know that Brownian motion is actually time homogeneous Markov chain, so I am not going to the 2-parameter family directly. I'm starting with the 1-parameter family. So this is the 1-parameter family. I'm just starting with 0 here and ttx. Okay, so this forms a contractive semigroup. Because it doesn't need a separate proof earlier from the earlier steps. We know that this forms a semigroup, and not only that, the norm is less than or equal to 1. These semigroups, so it is a contractive semigroup, and also it is a positive operator. Why is it a positive operator? Because if f is non-negative, the expectation is also non-negative. So this operator takes a positive function to a positive function. So it's a positive operator on this CBR. Okay, So next question is that what should be its generator. Okay, so the generator can be obtained from the very definition. Okay, if exists for some x, we write down a f x. Okay, if a is the generator, a f x is defined as limit h tends to 0 th minus identity divided by h f of x. Okay, so here we know that what is th, the semi-group. The semi-group is the expectation, this form. Okay, so we write down that, so THFX is expectation of f of WH given W0 is equal to x, correct? So we write down that expectation of f of WH given W0 is equal to x, and here minus identity, so that gives me only fx. Okay, so we have this difference. Now we have to compute this difference, correct? How do you compute it? We have seen in the stochastic calculus part that we can, so when f is smooth enough, we can apply Ito's formula. Ito's formula is the perfect thing to find out the increment of function of a stochastic process. So here f is, of course, in general need not have that sufficient smoothness, because f is only continuous boundary continuous function. Nevertheless, we here, for finding out this value, we take a much smaller subspace of CBR. Okay, much smaller subspace, so where we can actually compute it. When we can compute it, we can get a form of capital A which is valid for at least some smaller class. Okay, and then for other cases, we don't care much about that, where the limit would exist or what would be that thing, because I mean, when f is cis infinity functions, continuously, I mean, infinitely differentiable on compact support, or even we just take C2B as a C2C. I mean, so it is a twice differentiable continuously with compact support. Then also we can actually apply Ito's formula, and then we can find out this expectation that becomes finite, etc. So we can do that, and we get some form, and then we say that okay, the generator restricted on that class of good functions has this form. Okay, so and then we call that infinitesimal generator of the process W. Okay, so we do that here. If f is C2C, twice continuously differentiable with compact support, then as an application of Ito's formula, we can find out AFX is equal to half times f double prime x. Do you remember how to do that? So let us recall very quickly. F of WH is equal to f of W0 plus integration 0 to h f prime w s dws plus half times 0 to h f double prime ws, and then quadratic variation of w, so d of that is s itself, ds. Okay, so now if I want to find out expectation of f of wh minus f of w0, here given w0 is equal to x, so f of x here. Okay, so as x is equal to w0, so this is equal to expectation, so I close the expectation here, expectation integration 0 to h f prime ws dws. Okay, so this is one expectation plus the remaining part, that is also another expectation. I break in two parts for the ease of this. Half is there, 0 to h f double prime of ws ds. Okay, now if I have 1 over h both sides, So I write down here 1 over h here. Okay, now here in this this integration is 0, this expression is 0. Why? Because this integration here, f prime is bounded because f is c to b, correct? F belongs to c to c, that means twice continuous difference with compact support, so all the derivatives, derivatives are bounded, and then it's bounded, and then bounded function you integrate this to a martingale, then you get a martingale's expectation with mean 0. So this expectation is just 0. So you are left with only this. So this is the part which appears in a slide, and then this part should remain. And then as h tends to 0, so this thing would be, so here 0 to h f double prime WSDS, and as h tends to 0, this whole integration would be expectation. This is converse to expectation of half times f double prime of W0. Okay, so this is not random, this is deterministic. W0 is x, so this is half times f double prime x. Okay, so we go back to our discussion. So AF, which is f of WH minus WX, 1 over h and expectation, so that becomes half times f double prime x. Okay, or in other words, we say that the operator capital A is half times d2 dx2. Okay, so now for a similar reason, half times Laplacian is the infinitesimal generator of the multidimensional Brownian motion. So here I have just given one-dimensional case, but for multidimensional also same reason applies. So we get half times Laplacian. Okay, Laplacian is the del 2 del xi2, where sum over I is equal to 1 to d, where d is the number of the dimension. Okay. Next, we go further general case. So let script A be the operator associated with a time homogeneous SD, so which we have already seen earlier. When we have discussed strong and weak solutions of SD, we have discussed the operator associated with the SD. So if script A is the operator associated with a time homogeneous SD, whose weak solution we denote by xt. Okay, so weak solution is actually the triplet xt, wt, and the probability space and the filtration, but here we are suppressing those things, so just writing down the xt. Okay, so if that is the case, then we have seen a theorem. Okay, we are just recollecting that MF, okay, this is a process given by MFT at time t is defined as f of xt minus f of x0 minus integration 0 to t as, so here A is independent of time, so I should not write down S dependent, because we are talking about time homogeneous case. Okay, so this S is redundant. So integration 0 to t A fxs ts. So this whole thing as a function of t, this forms a process, and then stochastic process we denote by MFT, and then this stochastic process is a continuous square integrable martingale. Okay, so this we have seen earlier. Now in the expression of the generator of the semi-group also we have this difference. So fxt minus f of x0 can be written as this MFT plus this part goes there. Okay, so therefore fx, okay, where A is the generator of the so this X actually forms a strong Markov process, correct? Because when I have a time homogeneous SDA, the solution gives me becomes a strong Markov process with respect to the filtration. Okay, what is there? Okay, so for that, we can also discuss what is the Markov semigroup and what is the international generator of that Markov semigroup. So that we denote by capital A. Okay, so see, this A is just the capital A, the uppercase, but this is a mathcal A. Okay, the script A. Okay, so these two are different at present, are denoted differently. This A is the operator associated with the SD. Okay, so that is actually coming from SD's coefficients. If coefficients involve B and sigma, so this A also involves those B, sigma, those things. So I'm not recollecting the whole definition because that was done earlier. You can surely go back to the earlier video lectures and slides to see the definition of scripting. Okay, so now this AFX, okay, so far we are discussing now here, like, these generators. These are just, 1 over h expectation of f of xh minus f of x, okay, given x0 is equal to x small x. Exactly the same manner as we have obtained the infinitesimal generator of Brownian motion, okay. So now instead of Brownian motion, we are talking about some general stochastic process, which is weak solution of some stochastic differential equation. Okay, so now this f of xh minus f of x, from here we know that, okay, that can be written as in terms of m and then this part, m plus this part. But expectation of m would be 0, correct? Because m is just a 0 means square integrable continuous martingale. So that part would not appear here. So this difference expectation would be just expectation of this integration. So 0 to h, because h is there. So instead of t and t is there, now here h is there. So integration 0 to h, afxs ds. So that should be this, given x0 is equal to small x. Now here we have 1 over h and we want to take limit h tends to 0, right? Downward to 0. Okay, so here same rule applies, that since this is a, here we assume f to be function which is in the domain of a, and not only that, if it is a nice thing. It is giving a continuous function. Okay, so for that, if it is giving a continuous function, and then these things is also bounded. Okay, so we assume all these things. Okay. So for that, we get that this limit would be that 0 to h and 1 over h, as h tends to 0, would be just this integrand, and where s is evaluated at 0. Okay, so afx is 0. So x0 is small x. So the answer would be afx. Okay, so capital AFX is equal to script AFX. So capital A is equal to script A, as long as your small f is a good function. So here it is sufficient to consider C to C. So here, throughout this slide, I assume that f is twice continuously differentiable and having compact support. Okay, so A is script A. So we call, therefore, this is the infinitesimal generator of the strong Markov process xt. Okay, so here by this slide we have connected two different notions. Okay, infinitesimal generator of semigroup, what we were introducing in a deterministic setting from the book of Epazy, and another thing that when we are studying stochastic differential equations, and then we have came up with one operator which we call that, okay, this operator is associated with that SD. And now what we see that from that solution of the stochastic differential equation, if we find out the semigroup, that is nothing but, that is very easy, that is written in terms of conditional expectation, and from that semigroup if we find out the infinitesimal generator, then that infinitesimal generator, that operator, is same as the operator associated with the SD. Okay, so this gives the connection. So since this is connecting these two different operators, perhaps that Feynman-Kac formula, what we have obtained there, is also connected with mild solutions what we are writing down here. So this is the thing which I am now going to discuss next. Okay, so we continue. Revisit. So we are revisiting that inhomogeneous initial value problem. Okay, we have seen that the inhomogeneous initial value problem in the deterministic setting, okay, on the Banach space V. So here I am changing notations here a little bit, so to make both compatible and to compare these two things. So this ddt phi t is equal to a phi t plus gt. So this is the inhomogeneous initial value problem. You remember that there we have used f function, correct? Now we are using g function. Okay, and initial condition phi of 0, we have used small x, but I am writing small f. Okay, why? Because these members of the Banach space I would like to write down as a function. Okay, as a function, because this is basically Banach space which we are considering. These are like functions on the state space of the Markov process. Okay, so has a unique continuous mild solution, and that is given by the formula of variation of constants, that is phi of t is equal to ttf plus integration 0 to t capital T of t minus s gs ts. Okay, so this is the slide. Earlier we had this IIVP d psi dt is equal to a psi plus f, a psi 0 is equal to small x. Its solution, mild solution, was written as psi, this is psi, the solution, mild solution, ttx, the initial thing, and integration 0 to t, and then the semi-group t minus s fs ds. Okay, f appears from here. So we are doing that thing here. So tt minus s gs. Okay, g is here and initial is here. Okay, so this is borrowed from the earlier lecture, just last lecture. So where tt is the semi-group generated by A, and this G should be in L1, otherwise this integration may not make sense. Okay, is L1. So we have spent reasonable time and this discussion on these things. So the obvious counterpart for a terminal value problem. Why should we talk about terminal value problem? Because Feynman-Kac formula, what we have quoted, is for terminal value problem. So here, if we just change the time direction, then what should we get? I mean that is a very elementary way. So we can do that for every f in V. Okay, the terminal value problem. So we write down the value for terminal problem. D phi dt plus a phi t plus gt is equal to 0. Phi capital T is equal to small f. Okay, so if we change the time direction, then this comes here, correct? So the negative sign comes here. So d phi dt plus a phi plus gt, and then phi of capital T is small f. Okay, instead of 0, it is now terminal time capital T. I hope this notation would not be confusing. Here I am writing terminal time as capital T, and I am also writing the semi-group capital T, because semi-group always comes with the parenthesis starting. Okay, where for these final time there is no parenthesis which starts here. Okay, so has a unique continuous mild solution. Phi of t is equal to capital T. This is the semi-group. Capital T of capital T minus t, this is the time, final time. So instead of small t, I should write in capital T minus small t, because I changed the time direction. Instead of 0 to t, we have small t to capital T here. And instead of capital T of t minus s, we have capital T of s minus t, gs ds. Okay, so this is the time changed version. Okay, so now this equation can be compared with the equation what we have seen for Feynman-Kac formula. So we do that. If A is the operator okay, so if A is the operator of associated with a time homogeneous SD whose weak solution is denoted by xt, then phi t, where I'm writing a small x is just a point. Okay, so I mean point in the state space of the process xt. Okay, so you remember that here capital V is actually function on the state space. Okay, set of all functions on the state space. So those functions you can take bounded measurable or bounded continuous functions with sup norm. So with bounded continuous functions, sup norm gives me a Banach space capital V. So so here every if gt for each t, phi t are member here. So since these are member here, so this can be evaluated at some point small x, which is a point in the state space of the process. Okay, so we write down phi t of small x is expectation. So here whatever is written here, whatever is written here, I'm writing down the next page here. Phi t of small x, now capital T should be replaced by the conditional expectation, the capital T of t minus tf. So if I do that, I would get exactly this thing. Expectation of f of x capital T given xt is equal to small x, correct? Because this capital T minus t time difference. So this is the expectation f of x capital T given xt, and small x is the evaluation. Okay, phi t of x is equal to expectation of f of capital xt given xt is equal to small x, plus then integration small t to capital T of s minus t gs. So this we can write down as expectation of g of s comma x s given xt is equal to small x, correct? So that we do here, expectation of gs of xs given xt is equal to small x. Okay, so that semi-group of expression I am writing this way, and then integration with respect to s small t to capital T. Okay, so now we simplify a little bit here. So there are two expectations are there, this integration is there. So we write down expectation outside. So assuming that all these things expectation exists, then we can do this. So expectation and then this is interchangeable, so we can do that. Expectation of f of x give capital T plus integration small t to capital T gs xs t, sorry, this should not be used, should be s here, same as given xt is equal to x. Okay, so this conditional expectation is outside of these two expressions. So there are addition of two terms, f of xt and then this. So this is equal to expectation of f x. So now given xt is equal to small x, so that I write down as I mean the notation for the SD, because the SD which starts at time t at small x, that we write down f of x, the superscript tx given x subscript capital T, and here it would be also x superscript t comma x, because starting point is x at time t and s. Okay, and instead of g of s xs, I am writing g of s comma xs, because it's a function of two variables. Okay, so this formula, let us compare this formula with this one. Here we have written del v del t plus a t v plus g is equal to k. So imagine for our case k is 0. Okay, k is not there. So dv dt plus AV, and A is time homogeneous, so the A subscript T does not appear. So here this is our equation, d phi dt plus A phi plus G is equal to 0, and this is dvdt plus av plus g is equal to 0, so k is equal to 0 case. So there the solution is written as v is equal to expectation of f of x capital T e to the power of this, but k is 0, so e to the power of 0 is 1, so this does not appear. F of xt appears plus integration small t to t g of sxs and e to the power of 0 is 1, so only these two terms. So we also have obtained only these two terms. Okay, so expectation of f of xt plus small t to capital T g of this ds. Okay, this we have obtained from the formula of variation of constants, because this we have started from here. This is the formula of variation constants for the initial value. We have just time changed to the terminal value, and then we have just further assumed that the operator is associated with a time homogeneous time homogeneous SD, and for that we get a solution Markov chain also, and from that we just write down, and what we obtain is also a particular special case of Feynman-Kac formula. So this is the special form of Feynman-Kac formula for k is equal to 0. Okay. So therefore, the formula of variation of constants is a form of Feynman-Kac formula in a general setting. Okay, so by this I end today's lecture. Thank you very much.